want to welcome you to my lecture today. Before I get started today, of course, this is the week of a midterm one, right? Initially, I mentioned in the syllabus that I'm going to post the midterm um, between June 21 and June 22nd, which is open on Friday. But what I'm going to do now, I've changed my mind. I'm adding another day, so I'm going to post it on June 21 until June 23. So to give you more flexibility. But you know what? It is being programmed. If you are not ready to start, don't start. You can start at any time within the 48 hours window because the moment you click on start, your time is going to be running out. Does that make sense? And today, before the end of today, I'm going to post uh, midterm one practice questions with solution. And what is going to be covered in midterm one will only be what we did on week 1 and week 2. So whatever we're going to do this week will not be part of midterm one. Does that make sense to everyone? Okay. Now, today, the topic of today is diagnostics for simple linear regression model. Okay, so before now, you've been introduced to simple linear regression model, how we characterize relationship between two variables, assuming a straight line. I've walked you through how to specify your model, how to estimate parameters in the model, and of course, I've also walked you through some assumptions. Okay, but do you know what we want to do today? Uh, After we have estimated the parameters in the model, okay, how can we actually be sure of the validity of the model? Okay, I'm going to say that again. How do we ensure how valid is our model before we start using it in policy formulation? Okay, then we need to subject our model to to diagnostic. So, and that's why I call that diagnostics for simple linear uh, regression model. So in the outline, we're going to learn how to use residual plots to assess whether condition underlying the use of a model met. And I'm also going to walk you through some unusual observations. So let's get started. You know, every model in statistics has assumptions. And what make a model to be fantastic is when assumption hold. So what we want to do today is like, uh, what are the um, maybe procedure of assessing the conditions of model? Okay, that's exactly what I want to walk you through today. So every researcher need to do this. You know, we don't just use our model, we need to test our model. We need to investigate whether the assumptions underlying the use of the model hold. And that is what we call assessing the condition. Those of you online, can you confirm if you can hear me clearly? Okay, thank you so much. Thank you for confirming that. Okay, now I want to come to the numeric, let's say I'm going to start with the numerical summary of a regression model. Okay, now take a look at this. You know, when you run a regression model in R, you're actually going to have this output. Okay, now the question now is, what would you conclude based on the model summary? Is this simple linear regression model a good fit to the data? You know, we really we because with this output, when you take a look at this guy here, okay, we actually need those values to formulate our feeder model, right? The intercept and the slope. And I told you the other time, this guy here, if I really want to know how reliable is the slope, and now reliable is the intercept. I'm actually going to compare the p-value with the level of significance. Okay, and not only that, I also mentioned that the p-value here, if I really want to know how significance is the overall parameters in the model, I'm also going to investigate all of that. But let me tell you this. Most numerical results can be invalid when assumptions are violated. For instance, I needed to pay attention now. Do you know, even with all this, if you take a look at the p-value, if you take a look at this guy here, you know what is he telling us? He's trying to tell us that, okay, because the p-value here is less than 0.05, he's actually telling us the intercept is significant. Then when you come to slope, okay, when you talk about significance of slope, okay, the p-value here is trying to tell us that because it is less than 0.05, it's trying to tell us the slope is significant. And the belief in statistics is when the slope is significant, when intercept is significant, we're going to say, oh, our model is actually okay. And another thing is when you take a look at this, the p-value here, okay, the p-value here. The p-value here is confirming the overall significance of the model, okay? But let me tell you this, with all this, okay, this does not have to do with assumptions, okay? Even with all this that everything is good, we still need to investigate whether assumptions underlying the use of this model are met or not, because the moment the assumptions that we want to talk about right now, the moment assumptions are violated, okay, even though that this summary look promising, okay, we cannot trust our model. You know, it is more or less like somebody commits an offense in the state of Minnesota, right? And the person ran to Wisconsin, okay? And if a court in state of Wisconsin tried this guy and they are able to establish the fact that he commit the offense, do you know that whatever decision they take in the state of Wisconsin could be declared as null and void? Why? Can somebody tell me? Why is it that even though the state in the Wisconsin state was able to try the suspect that committed the offense in the state of Minnesota, even though they were able to establish the fact that he committed the offense, but I'm saying right now, whatever decision they take is going to be declared null and void. Why? Why? Can somebody tell me whether in person or online? Why? Exactly. Because he broke Minnesota law. That's a good one. Send me a message for extra credit. Because this person broke Minnesota law, it did not break Wisconsin law. So what Wisconsin is supposed to do is to repatriate that guy back to Minnesota. This is the same thing as this. Everything is looking promising here, but what is telling us is that Wisconsin does not have a territorial jurisdiction under the law to try the guy because the guy did not break Wisconsin law. The same thing in statistics. Does that make sense? So this may be promising, that may be significant. If you take a look at this now, the intercept is significant, the slope is significant, the overall, if you take a look at the overall parameters in the model is also significant. But if assumptions are violated, we cannot still rely on this. Does that make sense? Okay. Now, how do we investigate assumptions? That's what I want to show you right now. Now, investigating assumption, that will start from generating a scatter plot. Do you know that I told you something the other time that whenever you want to investigate relationship between variables, or particularly two variables, you need to first generate a scatter plot. Generating a scatter plot is going to give you an idea of the shape, whether whether you need to assume a straight line model or not. I need you to take a look at the first set of data. When you plot it, that is looking on average, looking like a straight line, even though we got some deviations, which is expected. Okay. Now, when you take a look at data set 2, okay, the data set 2 does not look like a straight line. That's a curve. When you make an attempt to use a straight line model, you're actually going to be wrong. Okay, it means if you use a linear model, okay, what happened there? Assumptions of linearity has been violated. The whatever result that come out of the model cannot be trusted, even though maybe some of these results may look promising, but they cannot be trusted. Now, take a look at the third one. The third that I said, actually looking like a straight line, but there's a particular point, this point, that is far away. That very point does not behave consistently with the rest. Okay, under this situation, we need to investigate for potential outlier. Outlier. You know, when outlier is present in a data set, it could be problematic to the model. Does that make sense? Now, I'm going to show you the data set 4. Now, when you take a look at data set 4, okay, you're going to see that this particular point, even though it is in the same line with other points, but that point is actually far away from them. If you compare data set 3 and 4, okay, this guy here is not in the same line with them. But if you take a look at data set 4, it is in the same line with them, but it's far away. Okay, now we actually also, so if you take a look at the two of them, they are anomalies that need to be investigated. Does that make sense? Now, I wanted to take a look at that. Okay, now take a look at, and I ask a question here. What causes issues in the model fitting? Okay, what causes issues in the model fitting? Okay, if you take a look at this, when model assumptions are violated, there will be issues in your model fitting. Okay, and if there's unusual observation, if you take a look at this guy, and this guy, they are classified as unusual observations. They also need to be investigated. Okay, if they are present in the data point that I said, there's going to be an issue. It could be problematic to the model. Okay, now why do I put them using a Venn diagram like this to tell you that this guy and this guy, they are mutually exclusive. They need to be investigated separately. The fact that you investigate this does not mean you shouldn't investigate the other one. You have to investigate both. Does that make sense? You know, I told you the other time, it is not as if our models are failing us. Our models are not failing us. We are the one that we're not doing the right thing. What is the right thing to do in model fitting? The right thing to do is to investigate whether assumptions underlying the use of the model hold. Then another thing is to investigate whether there's a presence of unusual observations. Does that make sense? Okay, so that is what I mean. Okay, now let me tell you this. Before we start analysis, we generate a plot. That is part of a preliminary investigation, and generating a plot will give us the idea of what kind of model are we going to fit, whether it's going to be linear or not. We got different kind of models in statistics. And do you know that? So that plot that we normally construct is called a scalar plot. Now, after that, after analysis has been done, maybe we fitted a model, we also sketch another plot. And that very plot will come is part of a post-analysis. We call that plot a residual plot. Now, do you know what I want to show you now? And I need you to pay attention. If this is a scatter plot for this data set that we constructed as part of preliminary investigation, after everything has been done, okay, and we want to have a post hoc analysis, this is the plot that we normally generate after everything has been done is what we call residual plots. Now, when a scatter plot shows a straight line, the corresponding residual plot should be without pattern. I'm going to say that again. This is what I mean. No pattern. Okay, no. Now, when residual show no pattern, you know what I mean? It means a straight line relationship exists. That's what it means. So residual plot is one of a diagnostical plot in statistical analysis. We use residual plot to investigate for linearity to see whether a straight line exists. And for relationship to be linear, for relationship to be a straight line, residual plot should show no pattern. Does that make sense? Why the scatter plot should show a straight line. So for this data set, that is a corresponding residual plot. Okay. Now I'm also going to show you a corresponding residual plot for data 2. Okay. Now I want to show you for all the data. I need you to pay attention for scatter plot for that data. The corresponding residual plot is this. For data set 2, the corresponding residual plot is going to be that. For data set 3, the corresponding residual plot is going to be that. For data set 4, the corresponding residual plot is going to be that. Now, the scatter plots are generated. They are part of the preliminary investigation that will give us the sense of what model to specify. Why residual plot is a post hoc plot, like after we've done, we've estimated parameters in our model and we want to investigate again, okay, the correctness of the model we've chosen. That's all. So we use residual plots. So residual plots are diagnostic plots. Okay, they are diagnostic plots. Okay, and there must be an agreement. Okay, now I'm actually going to be specific now. You remember the other time we work on rate my professor data. Okay, where we're trying to look at the relationship between quality and clarity of a professor. Okay, you know, this is the scatter plot. Okay, the scatter plot here actually showing a straight line, right? Then this is the corresponding residual plot. The residual plot for a linear relationship, residual plot should show no pattern. Can you see that? Okay. Now, the scatter plot is part of preliminary plot, the preliminary investigation. Okay, it's going to give us the sense of the model we're going to fit. And after we fit the model, after fitting the model, we also need to generate another plot. Okay, we're going to generate another plot. Let me tell you this, in a court of law, even though a court may have a territorial jurisdiction to enter a case, if a court take a decision, do you know an accused could actually call that a mistrial? Has somebody asked about that before in law? Like, oh, that this is a mistrial. Like, uh, maybe the decision they have taken, the accused doesn't like that, and I can say, okay, it can ask for a mistrial, stuff, a mistrial, stuff like that. Okay. So why are we all doing this? Why are we doing it? We're actually doing this to just make sure the model that we're using is going to give us what we want. And don't forget, we're actually going to take a decision based on the model, the result from the model. We form the recommendation from the results of the model. We form part of policy formulation. Number one, we don't want to waste our time. Number two, we don't want to mislead. Does that make sense? And that's why we're taking our time to make sure everything looks so good. But let me tell you this. If we really want to investigate whether assumptions are violated, I think we need to first understand those assumptions. I've walked you through the other time. But how do we test for this assumption? But before testing whether this assumption holds, it's better we also get ourselves familiar with this assumption. Number one, I mentioned linearity, right? Number two is independence. Number three is normality. Number four is equal variance. Before we can trust our model, I'm going to say that again. Before we can trust our linear regression model, all these assumptions must hold. And you can see all this assumption actually centered on the error, right? It's centered on the error. Okay. Now, what I want to do right now, a residual plot that look like, take a look at this. Does it have any pattern? No. Okay. This is more or less like a random noise. That is what we want. We want residual plots to look like a random noise. Okay. And if a residual plot look like a random noise, I'm going to tell you what we use out of the four assumptions. Don't forget, assumptions in linear regression, linearity, normality, equal variance, and independence. Okay, what can we use residual plot to investigate out of that? I want to tell you now. Residual plots can only can only be used to investigate assumptions of linearity and assumption of constant variance. I need you to take notes. We can only use residual plot to investigate assumptions of linearity and equal variance. Okay? We don't use residual plot to investigate normality. We're going to use a different plot to investigate normality. Does that make sense? We don't use residual plot to investigate independence, but we use residual plot to investigate linearity and equal variance. Okay, now what can you say now? By linearity, I'm actually going to say no evidence against that assumption, because as you can see here, this is without pattern. Does that make sense? Okay, now what about equal variance? We're actually going to say no evidence against it. Now, let me tell you what equal variance means. If you take a look at all those points, they are more or less equally dispersed. That's what I mean by covariance, equally dispersed. You know, when the values of S is increasing, the variance across is constant, as you can see here. So we're using this residual plot right now. I'm actually going to say we do not have evidence against linearity and equal variance assumption. But what about for normality and independent? And I said, okay, we cannot tell from the plot. Residual plot is not used. Okay, whether for normality or for independent, we don't use residual plots. We got a separate plot that we use for normality, which I'm going to show you. Is there any question moving forward? Is there any question here? Okay, now I have a question here. Which assumption is violated? Take a look at that. This is without pattern, right? But are they equally dispersed? Look at the dispersion here and the dispersion here. Are they the same? The dispersion is not the same. So what can I say? Here, that violates assumptions of equal variance. Does that make sense? If you compare the disparity across S, you're actually going to see here, it is clustered here, right? Clustered here, but here is spread out, right? That means assumptions of equal variance has been violated. Okay, but what about assumptions of linearity? Assumptions of linearity still hold because of the fact that, here, because of the fact that this is without pattern. But let's take a look at the other one. Let's take a look at here. Oh my God, this is with a pattern. Can you see that? What assumption is violated? Assumptions of linearity is violated. But assumptions of a constant variance is not violated. So take a look at that. That was why I said that violate assumptions of linearity. Take a look at that. Now, all these are residual plots. Do you know that maybe if I want to ask a question, I could give you some plot and maybe the residual plot, and I ask you to interpret that. Maybe I'm going to ask you to tell me which assumption is violated. Does that make sense? Now, I think I just walk you through how to tell from a residual plot if a certain assumption is violated. Okay, now before I'm going to move to unusual observation, let me first, let me see this. I want to see whether I prepare for testing normality. Give me 1 second. Let's check. Um, Oh, okay. Normality is not part of today. Maybe, because the diagnostic continue tomorrow. So the one that we haven't done now is assumptions of normality and independence. But what we've done so far is actually the assumptions of linearity and constant variance, which residual plots can actually be used. Now, where am I actually going now? Now, I want to talk about unusual observations. You remember the other time I said we should investigate for assumption. We should also investigate for what? Unusual observation. Okay. Now, when we say unusual observation, okay, outlier, okay, outlier is an observation with an extreme value y, okay. So the observation does not fit the pattern of the rest. No, it's not consistent with the rest. According to Benkamp in 1982, it's a data point that is not consistent with the rest. Okay, and let me tell you this. But what about the one? If I have an observation with an extreme value x, what is it called? It is called high leverage point. So observation, with an extreme y value is called outlier, but the one with extreme x value is called high leverage point. So whether outlier or high leverage point, they are classified as unusual observations. Okay, we actually need to investigate that in the, in a relational analysis. Okay, because if we don't investigate them, our model may not be trusted. Does that make sense? Okay, now um now you understand we could have an extreme value in y. When there's an extreme value in y, we call that outlier. When there's an extreme value in x, it's called high leverage point. Okay, now the question now, if I actually have my data, okay, how do I go ahead? Actually, okay, you mean like what if they fall within the y or fall within x? Okay, I understand because at time extreme value may not necessarily mean the me sorry outlier may not necessarily be the extreme at time, but there's a way we can actually detect that. So what we want to do now wherever the data is located, I mean, that anomalous or abnormality is located, we can actually detect that. That's what I mean. So, and that is what the technique I want to walk you through now. How do we detect that? Okay, wherever it is. Does that make sense? Okay, but what I'm just first trying to say now that most of the time it could be extreme value in Y or extreme values in S, but that doesn't mean it may not be in between, but wherever it can be located, we're actually gonna figure it out. Okay, and let me also tell you this: it is not all abnormal points that could influence the decision. Okay, so there are some that may, but how are we going to know whether a particular abnormality will influence or not? There's a way we can determine that. Okay, now take a look at this formula here. HII. If I really want to talk about I leverage, we're going to compute that. Okay, and we got a threshold. If you really want to detect, right, we need to have a threshold, which I'm going to walk you through. But let me first demonstrate this to you. Take a look at this. Everything okay, right? This is a situation where there's no problem when you take a look at this scatter plot. But you know what I want to do now? I want to add high leverage point that is not an outlier. You know, we have high leverage point, we have an outlier, right? Okay. An high leverage point may not be an outlier. An high leverage point may be an outlier as well. So right now, take a look at this. When you have this, okay, when you have this guy now, okay, when you take a look at this, I'm talking about this guy. Even though it falls on the straight line with the rest, but it's far away from others. Go ahead, yeah. Yeah, because if you take a look at this, if you take a look at all of these, to me, they are all like clustered, they are together. But take a look at that guy there. It's far from, even though it's on the straight line, the same straight line with them. In this situation, we cannot call it an outlier, but we can call it a high leverage point. Okay. Now, what we're going to do is, can this cause a problem to modeling? It may cause a problem, it may not. Does that make sense? Okay. Now I'm going to show you another picture now. Do you see that picture? I'm talking about this guy. It is not on the same straight line with them. That's a potential outlier. Does that make sense? That's a potential outlier. It could be problematic to the model or not. So what am I trying to show you now is just like, how do you detect abnormal data points graphically using a scatter plot? Okay, that is it. But using a scatter plot is not enough to say that they're going to cause a problem. But this is just to detect. It's just like a police that is on patrol, they stop a vehicle, right? That doesn't mean the driver will be punished. It is not all the vehicles they stop that the driver get punished. Does that make sense? That's what we mean. Okay, now, do you know we can have a situation where we can have an outlier that is also a high leverage point? That is not good at all. And this is the situation. Okay, this guy here, do you see this guy here, right? When you have a situation like this, I normally call that a double tragedy to the model, a double tragedy that need to be seriously addressed. Okay, now when this happen, what happened? Now, mathematically speaking, statistically speaking, what are the measures of detecting outliers? Okay, number one is to use residual. You know, residual is the difference. You remember the other time, right? Residual is the difference between or the original and the predicted, right? The gap. Okay. Now, another way of dictating outlier is using a standardized residual. Standardized residual. If you take a look at this, the error cap, that A cap is the distance, y minus y cap. The sigma cap is the estimated standard error that I show you in the output the other time. What is the HII? You remember I showed you HII today, right? Okay. Now that is another way to detect an outlier. Okay. Now, of course, this is a fitted, this is a regression, the residual plot. Now, this is the variance of the error. Okay. And this, we use this. This is a typical picture of a residual plot that can be used to dictate an outlier. You can see here, this point, right? It's far away from others. That indicates outlier exists. But let me tell you this. There are so many ways of detecting outlier, residual, standardized residual, and so on. But the most commonly used measure of outlier was given by Cook distance. Did you know that somebody who discovered this, okay, actually is a member of a School of Statistics, University of Minnesota. It's my colleague. Okay, so an emeritus professor. Before coming to United States 10 years ago, I heard about Professor Cook. You know, Cook distance is actually a modified and a robust measure of detecting an influential point. Look at that, influential point. Okay, we are interested in outlier and high level point that are influential. Influential means that could be damaging to the model. Does that make sense? Okay, now I need you to take a look at this. DI will represent a particular Cook distance value. And what do you think this man did? You know, in the formula, what do you see? You see ROI, you see HII. Let me take you back. Let me take you back. You're going to see. Do you see this guy? That standardized residual is in his formula. RI and the HII is in its formula. And that is why it's actually robust, this approach. Now, this man curated, the Professor Dennis Cook actually curated a threshold, okay, for us to be able to know. Now, take a look at this. A large Cook distance means observation is more influential. And what is a threshold? We need to investigate the cases with Cook distance greater than 1. This is the formula to find the Cook distance. Okay, it means if you have 20 observations, how many values are you going to have for D? 20, D1, D2. Now you want to identify a particular one that is more than 1. Does that make sense? The one that is more than 1, then we're going to trace that to a particular observation that we're actually going to call an influential point. Now we want to investigate right now. Take a look at this. When we have this guy, okay, it's a high level point. We computed the DI, and the DI gives 0.03. What is the meaning? Then it means it's not influential. Because what is the threshold? D is 1. So for it to be influential, it has to be greater than 1. Okay, so even with this, there's no problem. It's not going to be damaging to our model. Does that make sense? Okay, now take a look at, I'm going to show you another one. Okay, here we actually suspected an outlier. We computed the Cook distance that gave us 0.41. There's no problem. It's not going to be influential. That's what it means. We got a threshold, right? Then I'm going to show you another one. Give me 1 second. Show you another one. Okay, here, this is like a double tragedy, right? Let's take a look at it. Oh my God. D is 4.7. This is actually, and when I say D21, you know the meaning? It means observation number 21 is an influential point. That's what it means. Does that make sense? Okay. Now, Now, when we dictate an outlier, like my TA will actually walk you through a lab, how to, when we dictate an outlier, for instance, how do we deal with it? Does that make sense? Because it needs to be addressed. Okay. Now, what are the strategies for dealing with influential observation? Okay. Number one, simply remove. But let me tell you this. This is what I did for my PhD work that I defended in 2016. I argue against removing an influential point. You know why I argue against removing it? Because it's a genuine observation. It's just like I conduct an exam. Maybe I have 10 students in my class, and 9 students score above 90, and somebody scores 0. If I want to compute the class average, am I going to remove the score of somebody that scores 0? No, because it's a member of the class. So what am I going to do is to look for a more robust way, a more robust method that can accommodate outlier. Does that make sense? In such a way that even though outlier is is in need, but that particular model we ignore, we actually address that in such a way that the outlier will not be influential. Okay, and that is what I mean here. And it fits a different model. Okay, actually set up a different model that is robust, that can actually accommodate our outlier. Does that really make sense? Okay, then another way is you have to look, before you know what to do to outlier, whether to remove it. Do you know the one you can remove? To the one, maybe when you are collecting your data, you make errors in recording. Okay, maybe you wanted to write 500 and you write 50,000. Of course, you can correct that. You can remove that. Before you actually going to know whether to remove or not, then you need to identify the cause. Does that make sense? The one that I argue that cannot be removed is the one that is through erroneous imputation. Does that make sense? Now, do you know that a cause of outlier could be as a result of incompetent lab assistants? For those of you who are making recordings, okay, maybe the lab assistant did not set up the equipment the right way, and then definitely there's going to be errors in readings, significant errors in readings. Does that make sense? So you got to make sure that the lab assistants, taking your measurement is actually competent. And another thing that we may be having, maybe a geologist searching for oil deposits. When you are searching for oil deposits, at times it took forever to be able to see that. And as time goes on, then you started seeing all of that. Okay, I'm going to demonstrate something to you practically now. We have S and Y, and I deliberately plug an outlier. Who can sense the outlier in this data point? I plug an outlier. Where is it? This on this. Whether you are online or in person, can you identify outlier in this data point X and Y? Where do you think it's going to be? Oh, look at number 21. Do you see 4? Look at others. And let's see whether we'll be able to detect that. Let us plot this data. Can you see that? You see here, right? Can you see? Okay. That is generating a scatter plot. What code did I use? This is the code in R. Okay. This is the name. This is the code. This code is maybe because I have my data in CSV or in Excel, I convert to CSV command delimited, then I attach, then I plot. Okay. And when I plot and I do the outline is just to see the straight line, I have this, and you can see the data point here, right? Okay. Now let's do some diagnostics on this data. Okay. We want to see what is going to be the residual, what is going to be the standardized residual. Take a look at this. Okay. You know, it's identify observation number 21, like I said. Okay, and that very observation, the residual is very, very large compared to others. And not only that, the standardized residual is also going to be large. So, I told you the other time, one of the primitive approach for identify an outlier is when a particular observation has large residual or large standardized residual. Okay, so this is the code. Recede. This four of us getting the error for each observation. Recede is a coding now. Recede is just original Y minus predicted. Which one is large? Oh my God, do you see that guy, right? Number 21 is the largest, right? Okay, can you see that? Okay, what about the code for standardized residual? This is the code. You're going to write R standard into that. What look, can you see the red flag, right? Number 21 as well. Okay, using residual, it pointed out to observation number 21. Using standardized residual, it actually flagged observation 21. Using the Cook distance, okay, using the Cook distance. This is a code, okay, that is Cook's dot distance into the model. And a Fleischer point is actually going to be the one that is greater than 3 mean of whatever, and what happened? It flag out this to be Fleischer point, observation 21. And you can see there's an agreement, right? There's an agreement between the residual way of investigating that, the standardized residual way of investigating that, and a Cook distance way of investigating that. Now, why should we care about outliers? Okay. Why should we care about outliers? I said we should spend an awful lot of time worry about outliers. Okay. But why should we? Okay. What impact does their existence have on our regression analysis? Let me tell you something. If you don't investigate them, they could be problematic to the model. And whatever decision you take at the end of the day, you're actually going to regret it. Okay. Now, let us try to do our data set. If we regress Y on S with data set without the outlier, I want to show you something now. Do you see the model that we got, right? Without outlier, you see what we got? Now, with outlier, is that a different model? This is 2.96, 5.037, but right here, they are not the same. Can you see that? So another thing you're going to see, you're actually going to see in the R squared, okay? With outlier, R squared here is just 91%. Without outlier, 97%. Which one is better? The one without outlier. And what did I call R squared the other time? R squared measures the contribution, the percentage of variation the model can explain about Y. Does that make sense? Okay, so what have we done today? I've walked you through how to investigate regression model. But we're going to continue tomorrow because I know there's going to be another material for that is designated. Oh, go ahead. Oh, okay. Uh, when I get there, you tell me, okay? Where? Okay, should I keep on going? Okay. Oh, the HII formula? Oh, okay. Let me go there. I think I know where you're talking about. Oh, right here. That one? You're welcome. But it's also, this material is published, so you can also access that. Okay, so this is where we're gonna stop today. Is there any question from those that's also attending online? Is there any question? Okay. Make sure you all stay safe and have a lovely day. Bye for now, everyone. Yep. Bye.
Thank you.
You're welcome. You're welcome.